Thank you, and thank you for the organizer for inviting me, especially Juan, and for half of the audience for following me from Ghent to be here. So I'm going to talk about what I call the where's the talk? Called the fractal. A Goodstein principle. And this is joined with Andreas. So I'll start with some fairly recent history of new variations to Goodstein's principle. So for me, in about the last 10 years and maybe in the last 15 years or so, there have been some efforts to revisit Goodstein's principle and get several improvements, several refinements from it. But this specific talk is focused on raising the strength of Goodstein's principle. So Goodstein principle is a principle about the way we write natural numbers. And in the standard way, you would write natural numbers as some sort of at n some sum of powers of some base. Normally we use base 2 or base 10, but for Goodstein principle, you sort of go through all the bases. And this way of writing natural numbers leads to a well-founded principle that is related to the ordinal epsilon 0. So in recent work with Andreas and also Rai, Weiner, if instead you somehow write down natural numbers based on the Ackermann function, now we use a funny version that let's use like this. So what we're going to do is add an extra parameter. You're used to Ackermann functions having 2 parameters. This new one is what we call the base, and it dictates how many times we iterate at each stage. So this would be, in the generic case, the previous value, and you take the previous value of the right input, and then you iterate the previous function with respect to this input many times, right? The standard version will have a 1 here, but it works for any number, and this sort of plays a role of the base notation system, and this leads to the principle of strength gamma naught. And most relevant for, so what if you want something nice and juicy like Bachmann-Howard ordinal? So if you follow this line of this basic evolution, you will think, well, I need a faster growing function here. And what's going to happen is that you use some variant of the fast growing hierarchy for epsilon 0 with more or less, very roughly, the idea is that if you have something that looks like this, then that'll become collapse. Collapse. More than that depends on 3, right? Very, very roughly. So, yes, we have Goodstein principles of high proof-theoretic strength, but I think part of the magic of Goodstein's principle is that from very basic operations in natural numbers, you suddenly get these transfinite numbers. And here, well, yeah, you are getting more transfinite numbers, but you already fed it transfinite numbers to begin with, so there might be some room for improvement. So I'm going to go back to this, and first I want to state the basic idea behind writing numbers with a certain base, with the standard exponential that we're used to, comes from the arithmetical fact that every number can be uniquely written like this, where you have this, n is positive, by the way, and a is less than the base, and r is less than b to the e, right? So this, if you write 6 in base 2, that'll be 2 to 2 plus 2. This will be, you got 1 in there, and this will be my r, my a, my e. Base 2. Now, the way the theorem works is you say, well, what if this 2 suddenly became a 3? So what we're going to do is define some sort of operation that replaces 2's by 3's, and that will clearly give me a much bigger number. So in general, if c is greater or equal than b, greater or equal than 2, we define the base change operator on some number n. Suppose n is written like this. And that's an inductive definition where you have a recursive definition. You apply the base change to the exponent. You apply the base change to r. And this is, I think, kind of a funny operation because this is just making bigger and bigger numbers in a way that at first sight might seem chaotic. So in this particular case, we would get something like, we get exactly this. Where? B to the E. Less than B to the E. And A is less than B, but R is only less than B to the E. So this is a digit, and this is just the rest of the number after the main term. And okay, so then the theorem, Goodstein's original theorem, which I think most people find surprising, is that if I define the following sequence, you fix n a natural number. By the way, 0 is just fixed, so you do need a special case because 0 doesn't have a decomposition like that. All right, so you define g0 of n to be n, and gi plus 1 n to be base change. So base 0 doesn't make any sense, base 1 doesn't make any sense, so we're going to always add 2 just to make sure that we're starting at 2. That's the only reason for this plus 2 here. And we raise the base by 1. And the key here, this seems very innocent, but it is absolutely crucial, we subtract 1. And the way I set it up is that gi plus 1, 0 is undefined. Sorry, that's not quite right. gi plus 1 undefined if gi 0 is 0. So the way I'm going to set this up is that these sequences could in principle be finite if I reach a 0. Then I cut them. Theorem. Goodstein. For every n, there exists an I such that gi of n is equal to 0. And it was shown by Paris Kirby. Goodstein's theorem. Independent. So that's our starting point. And again, there's other results, but somehow we're going to stay very, very close to this one. We're not going to work with Ackermann functions, fast-growing functions. We're going to stick to the exponential. And we're going to think about how we write big numbers. But when you see this kind of talks and you say big numbers, you imagine something so big that you could doubt that it even exists. No, I just mean like astronomically big numbers. Big numbers, but that you can still write down. So if you have a number in base 2, I don't know, you will use look like this. And I want to observe that the digits that will appear here are these two. You have a number in base 10, and again, I want sort of a big number, but nothing that I can't write down. Then the digits that I will see here are going to be everything from 0 to 9. And here I want to stress that these symbols, we memorize them. We memorize their multiplication tables, which are 100 different entries. If we all use base 2, learning our multiplication tables would have been much easier. But this is still a bit of a long expression, and you could ask how I could shorten it. So the typical thing we do is that if this, for example, is an expression in meters, I rewrite it in kilometers, and I'm just deleting a few digits, right? That's a very mild change. If the number has 100 digits and all I'm doing is removing the last 3, that's not going to make a big change. But something we don't see very often is, what if I wrote this in base 1000? So if I wrote this in base 1000, this would be about a third of the length. But what would be the cost? I'm going to use m for 1000 in Roman. The cost is that now my digits are quite a few. So if we were going to use this base 1000 system for writing numbers, we would have to memorize 1000 different digits. We would have to memorize 1 million entries in a multiplication table, all divided by 2, I guess. So that doesn't seem terribly practical, but I do want to make a little observation here, which is that here I'm allegedly representing the digits for this base 1000 notation system, but you notice that I just instinctively wrote them in base 10. So that could help us to not have to memorize 1000 different digits. So in such a context, you could imagine how numbers that have, about 100 digits get written in a certain base, numbers that have about 10 digits get a different base, and numbers that have up to 3 digits get a different base. So you have a hierarchy of bases. And the first base must be at least 2, because you could talk about writing numbers in unary, but we don't like that. So these are going to be sets of natural numbers that don't include 0 or 1. And such that for all we want later bases to be multiples of the earlier bases. I need to find a good story for why this is mathematically very natural, but at least it doesn't seem that weird. But the honest reason is that something in the proof doesn't work if I don't assume it later. So that's our base hierarchy, and how do I erase? Because this is not a philosophy talk. Or, I guess I'm expected to not erase, right? So this will be a philosophy talk.
Pushing the problem under the bar.
So,
you'll have to face it eventually.
Sorry?
You will have to face the problem.
I will have to face the problem, and there's always. All right, so I have a base hierarchy, and I'm going to use this to represent natural numbers. So every natural number will be assigned a base. Now I said that I don't want to use unary, so I have the least element of B, which maybe I'll call it B0 for now. Then maybe I have some B1, and so forth. Normally, if I have a number here, I will write it with respect to the biggest base available. The base itself will usually be written with respect to itself. Sometimes I will use a previous base, but for now, with respect to itself. But like I said, I don't want to use base 1, so all of these I decree to be written with respect to this base, even though those are just digits, right? So that's to the minimum. Right, so it's just what I think what I said in words is easier. Right? So just take the largest available base, except that if you're below the minimum, you jump up to the minimum. Yes, that's because this should be max. Thank you. Oh, the definition will require non-emptiness. So you always want there to be at least one available base. And then that's what we define. All right. So let's take a number such as let's take our base to be 110. So if I want to write the number 150, that's going to be 100 plus 50 and plus, and that's a 10 times 5. But now I notice that these two are smaller than 10. So the base that I write them with is 2. So that becomes, actually the 2 just kind of looks like itself. But 5 becomes 2. Right? So I'm writing the number in base 10, but I write the digits in base 2. And again, you can imagine how if I include a much bigger base here, then that lets me represent big numbers, especially big numbers that have lots of zeros in their representation will have some compression in such a setting. Okay, so we want a Goodstein theorem for these things. And let me see. I don't know, if C is 330, 180. what would it mean to raise? So first of all, if I have a number written like this, I want to raise the base, then somehow I will raise the 100 somewhere, I will raise the 2 somewhere, right? What was before raising one base to another will be, I call it upgrading from one base hierarchy to another. And you can imagine somehow that the 2 will become a 3 here. But when exactly are we going to use 30 as a base? When exactly 180? This is this can be a little bit tricky. So what we're going to do is the following. We define, let B and C be base hierarchies. Define these two are functions from naturals to naturals. So let's take this number here, and this is written with respect to base 2 and base 10, and we want to raise the bases to match up with this. So you can imagine that 2 will simply become a 3. So this will sort of become, but now you might notice a problem. Yes, sorry, you're right, this is 3. Now you might see that we have a little bit of a problem here, because this 10 is smaller than the digit I put here. It's kind of fine, because we have this 30 available, so 30. But now you will notice another problem. So this is my base hierarchy. This is what I'm using to write numbers. If I ask myself, what is the base that I'm supposed to write this number with respect to? It's actually, I mean, quite a bit bigger than 180. So I should have written it in terms of the base 180. So that's sort of a forbidden notation somehow. I cannot write up such a big number with respect to a base that went before another base. So that's fine. I just skip the base, and we go straight. And this will be the upgrade of.
What's the problem with 30?
That if once I put 30, I get a number that is bigger than this base here that's available, right? So what was the rule? That to write down a number, I look at the biggest available base and I use that. So then this, with the 30s before, is a bad notation because it's not really the way I'm supposed to represent that number. I'm supposed to use this one. So I say, okay, fine, I'll skip it and use this one instead. They could go quite a bit. In fact, there is no particular reason why this operation is always going to be well defined. So if you can imagine that if the bases are very tightly packed on the C side, then it's just going to push on forever. So we will make that restriction that they can be infinite, yes. But I will have to control that they're match well, because you do have hierarchies that don't match. I will give an example in a second after I give the definition of these operations. Right, so the moral of this step here is that somehow we have to consider an intermediate step where we're raising the base after we've already raised the basis of the coefficients. And then we sort of test. So that's what this operation here will do. Let's write the definition. 0 always just stays as 0. And then now let's suppose that are defined below n, and the first thing we're going to demand is that this doesn't happen. We will, if we notice that a digit became larger than the base, then we'll immediately try a bigger base. So C has to be greater or equal than the upgrade of the. So I should say is a base. And suppose we've already defined this operation and the upgrade. Define if n is fine. What are we going to do? We change the base, as we would for Goodstein. Whatever this operation did, we do it here. Notice that E could possibly have the same, E could be quite large, it could have the same base. There's even examples over there, 2 to the 2 has the same base as this. But A is a digit. So we are going to move digits, but now they're treated as something that's already been completely controlled, and we apply the final version of the base change. And to the R, we also apply this sort of provisional one of testing the new base. Once we've done this, then let where C is least, so that we want to make sure to be at least our previous value. We want this to be increasing. We'll introduce this notation. This is a capital C, where right. So this is a successor with respect to the base of C, so the next base after C. We accept this to possibly be infinity if I already had the last base, that's fine. And but normally it's just going to be whatever came next. Yes. So C is the natural number, which is at least what the base already rose to. So if you take, let's see, you take here, you take this number has base 10, right? So you would first raise the number 10, and then whatever value you got is the least possible value that you will assign to this whole number. This is because we want to keep the operation monotone. Now, one very good objection would be that this is not always well-defined, and that's absolutely true. That's fine. We'll address that, but Yes, did I forget? Yes, I forgot to put that maybe. On the right board.
No, right. What are you saying?
On the right of the board. Okay.
Right off the board.
Okay. Right. Which this C is still the same C. Well, it's still one of these possible C's. So it belongs to the basis. Yeah. So you have a fixed selection B, another fixed selection C, and you want to upgrade numbers written with respect to B to numbers written with respect to C. So you're going to do basically the base change of Goodstein that you would do for the normal Goodstein until you somehow are getting a value that is too big and goes beyond the next base. So then instead of going a little bit beyond the next base, you go all the way up and raise with respect to that base. Which is what happened here, right? So we tried raising this number to base 30, but we noticed that we got something bigger than that. So now we use something much bigger than that because we are using this as a new base. Okay, so this absolutely will not always be well defined, and now this will no longer be a philosophy talk. Do I use these?
I will give you a tutorial.
Okay.
And everybody. It's an unsolvable problem. We'll postpone the tutorial.
All right, so F, B, C are base hierarchies. C is a good successor for B. So maybe it's good to I often will use this notation to clarify the basis I'm using. Well, so this might seem a little bit unsatisfactory because we're never going to justify that this somehow is always defined. No, it isn't. It very often is not. But we will restrict our attention to cases where it is. And this condition is the one that's a little bit. So when we're applying the upgrade operator, we might have some very big jumps between one number and the next. That's fine. But we don't want the bases to be responsible for the jumps. The bases are just placeholders. They're controlling the process. They're not the places where things are going to go chaotic. Things are going to go chaotic because I'm taking a number that has exponents, and it might have a tower of exponents, and I'm raising something, so that's where the growth comes from, not from the bases themselves. So these have to be a little bit, will be behaved in the following sense. If C is a base of some number, and n plus 1 happens to be a base, or let me just write this one. The least base has to be at least as big. then there is multiple. C in so the bases have to be multiple, so the previous basis, you see there's some sort of critical behavior that's going to be happening at multiples of the basis, and we don't want these to just be skipped completely by the base change operator. So if I have a base, that's not going to skip any critical numbers here. This particular condition, I hope, can be weakened somehow in some future version, but if you don't object to these, then that's all I need for the theorem. Yes, I could use that board. Do you put some water here, or?
Yes.
I will be forever amazed at water-based blackboards. Thank you. All right, so what was I saying last? Oh yeah, that's all. That's all you need to know. So definition: if it's a sequence I take such a sequence, it's a bunch of base hierarchies. I'm going to base my new Goodstein process on these. And I always want the passage from I to I plus 1 to be a good successor so that the operations are well defined. We say dynamical base hierarchy if for all is a good of the I. And that's it, the theorem. Theorem 1 is that if B is a dynamical base hierarchy, and I will use this abbreviation sometimes. Fine. You remember we had the Goodstein process before, and now it has this parameter B by BI. We start at N, and what we do the next step is we do the upgrade operator on GI. And we subtract 1. And as before, undefined if d I b n, then this always reaches 0. And I realize this probably should have been a definition and a theorem, but it is what it is. And the cool thing is, all right, so let's see if the tutorial worked. But this fact is not provable in, I'd like to say KP, but anything of Bachmann-Howard strength, ID1, or all these. Right? The base, you could assume that it's computable because the incompleteness. Yes, this looks like a pi11 statement, but the incompleteness is for concrete recursive piece, which actually is an interesting. I haven't explored that direction. If you really let it be a parameter, you probably do get a nice pi11 independence. I mean, you get it because it implies the computable version, but you might get something that's actually, equivalent to the pi11 reflection for the theory or something like that. Right, exactly, yeah. So if you let the B vary like this, it should also be equivalent to well-orderedness. Bachmann-Howard. All right, so how do you prove well-orderedness that Goodstein's theorem, the original Goodstein's theorem? What you're going to do is you're going to imagine that this base change that we defined can also be defined for omega. So again, and all of these operations we have available in this original setting are still available in the transfinite setting. And you have to check the following properties. And 2 less or B less or equal to C, then what does this one mean? If I take a number, I write it with respect to base B, and then I replace the base by omega, it's going to be the same as if I take the number, I replace it by some larger base, and then I replace that by omega. And the reason for that is that the structure of these normal forms is maintained. If I put a C here and the C is larger, then I will still have a smaller digit than C. The digit didn't change, and you could check the rest of the properties. So this intermediate step will basically not do anything. And from here, I get an independence, a termination proof. Again, this for the original Goodstein. As follows. So remember that gi plus 1 n was g plus 2, 3, and Di and minus 1, right? So if I look at what this becomes, here I would have this number is written in base I plus 3. If I consider its omega base change, that's the same thing as the omega base change of this, so that's the definition. That is less, and now I'm using this property, then just take this. And that is the ordinal that I assigned to the previous guy. So if I look at these ordinals that I'm assigning, in the sense that I take the current base that I'm using and I replace it by omega, I get a decreasing sequence of ordinals, so this must be 0. We're going to do the same thing. And so we want an ordinal assignment that is monotone, but based on these base hierarchies. Let's see what I learned about that. The thing is, this is the oldest board. So I'm going to stick to a running example of and we have here. Let's just look at simple number. I want to do the same thing I did there. So if I'm in the, by the way, I forgot to mention this. Suppose I do this. I define a dynamical base hierarchy where each base hierarchy is a singleton and it just contains the number I plus 2. Then this is just Goodstein. So the original Goodstein is a special case of this, where each base hierarchy has one element. And what you said, you could also make the elements grow faster, and you'll still get no matter how fast they grow, it's still going to be an epsilon 0 in this result. But as you start to get more and more bases, you get a bit more complexity. So if I have something just written in base 2 over here, 2 plus 2, let's say, I raise the base to omega, what I'm doing is just putting omegas wherever I see. So if we try this, and just wherever I see a base, I put an omega, I would immediately see that monotonicity is failing, because that is the same ordinal that I am assigning to the 2. So just the base omega substitution that we did before is not going to get us anywhere here. I'm going to think as follows. I don't know what ordinal I assign to 2 to the 2, but I will call it OB of 2 to the 2, and I will assume only that it's countable. So what I want to put here is something that's large enough to make sure that this sum doesn't cancel out like I have here. And okay, so a safe choice is, let's go an uncountable value. All right, so actually this will be a useful ordinal. I will call it capital O. But the assumption was that I was assigning countable ordinals to this, and if I just leave it uncountable, I just ruined what I was trying to do, right? So let's try collapsing it. And I'm not going to talk too much about psi. Just let's say, okay, we collapse it. Now it's countable. And that's going to be very close to what we want to do. But here's what happens when you have many bases. So you have 2, you have 10. The shape of this ordinal has to do with how far I am from my base. So if, for example, I take something that's over here, very close to 10, and something here that's just above 10, then this will look like a small ordinal, and this will look like a big one. So for example, 10 would naturally be mapped to just omega, because 10 has base 10. But let's just go with 4. That kind of looks like omega to the omega. So again, monotonicity fails. And that's going to make the psi function not be great. So instead I'm going to use theta function, and I have to speed up a little bit. But what is the theta function? For it's the least power of omega, such that I'll write it down and explain it. Where how's it? All right, so if you write a number based on capital omega, exponentiation, addition, and multiplication, you will see some countable ordinals appearing. The largest one is going to be this theta star, by definition. And then you want the theta function to be greater than all values of theta functions below for ordinals below, but only those ordinals below that their maximal coefficient is bounded by your value, the theta function. If you hadn't seen this before, I think this one's a little bit hard to get used to at first. But the only thing I want from this function is the following property. So first, this converges to P, and how do I compare values of the theta function? I take the smaller one, I take its maximal coefficient, and I check whether it is smaller than the theta value. What is the moral of the story here? I could take a very small ordinal and make its theta value be very big if I sneak in a large coefficient in there, and that's a trick we're going to do to keep monotonicity. So right, so I'll just go for the definition because we're let E be a base hierarchy. Define so I said I will sneak in a large coefficient. This large coefficient will be this one. This will ensure that I don't have that that problem over here with lack of monotonicity. So let's use that one. You won't see it in this example, but this ordinal will typically be uncountable. This will be its theta collapse. Okay, if we look at the base of n, and we define the following ordinal. Right, so this just replaces the base by omega. And now we're almost done. We have two cases, and it's not in B. That's just going to be the big ordinal. No, here we want to cheat a little bit. Let's put a -1 here. For elements of the base, we're going to do the following. We're going to write it with respect to the previous base. And finally, either 0 if the top thing is not defined, otherwise it's and all right, so this is going to pick up whatever values I have from below, and we sneak it into the coefficient as follows. Right. Okay, so yes. So oh yeah, the theorem was stated long ago. Oh, Bachmann-Howard. I said that.
Okay.
I said that before.
You didn't state the
I did. Theorem 1 was this terminates. Theorem 2 was is not provable in KP.
Oh, right.
And so the point is that this assignment is the one that has these properties. And like this. With these two properties, you could literally follow the proof of the original theorem. They're not easy to check, but the big journey is this sort of reverse engineering process which is very typical of Goodstein type results. And yeah, so there was a lot more I want to say, but no, it's not enough. So I'll leave it here.
Say something about how you
Yes. You want to give me another talk? I'll give another talk then. Because it's at least it's about this degree of complicatedness. Deals. I was hoping you would know. So these three results that I showed at the beginning for Ackermann, for a fast-growing function, should be it should be possible to combine them here. I was first optimistic that you would get some big blow up, like if you have a fast-growing hierarchy, then omega would become something like an inaccessible. But now I suspect you just get that function on top of one uncountable. So for example, you might get one uncountable with a gamma function or something much tamer. So I think going beyond requires fiddling more with how does B's work and not so much with just the functions available. Good.